Okay, let's get into lecture 4. So you've had a chance now to go through the lab and do a model that is no longer national production, even though that's probably what I'll keep talking about. Um, and but you see how this works, how to get a solution, and I think you were given some steps to make some changes and see how the solution changed, and that's what we want to think about here. So let's remember, we're talking about confirming supply theory via the GDP problem, the idea that relative prices matter, but really starting from an allocation based on GDPA, where prices have one level, one relative level, and then some price change that drives us over to GDPB, and this combination from the start of the arrow to the end as the solution. And that's key in economics. That's supply theory. And if you were to ask an economist, what we're demonstrating here would be elasticity. So the own price elasticity of supply. And it would be an important thing to try to measure how that quantity adjustment happens when prices adjust. So if it is the case that elasticity is important on these, and it can be measured because any small price change will cause us to adjust the output, well, that's something we're going to lose when we move to these corner point type problems, these linear segmented problems. We are not going to have an elasticity measure because we've already seen that you can make small price changes here that cause nothing to happen, and then eventually you get to a small price change that causes the allocation to jump. It could be the tiniest price change, right, given the starting prices, and just a very small price change moves you from B to C. So a large change, no change, no change, no change, boom, you move down to C. And so that's really the conceptual idea around price sensitivity in an LP, and one of the things we have to come up with an approach for to be sure that even though we can't calculate elasticity and convey that sensitivity, right? How sensitive is my output choice to the price level? How quickly or how aggressively do I respond by increasing output when prices change? So in this context, we have to think of something else. And so the starting point here is to think about an initial corner point solution. Let's just call it GDP line 1 up here, that gave us allocation B, and then some rotation, right? Until eventually you rotated enough that you would want to jump from B to C and get a new solution. And so that could be represented roughly on as sort of an average result by GDP line 2. And if price changes keep going in that way, right, you keep sort of thinking about this rotation where food prices are going up relative to non-food, well, nothing happens over some of the price changes until eventually, though, to get the strong enough price reaction, you will see this economy go from this combination of outputs to only food, at least as predicted here, right? Because we have an economy that thinks about food and non-food and measuring the value of those to maximize GDP. So if normal economic problems with differentiable and smooth continuous functions really key towards the idea of an elasticity as something you're going to measure, maybe even do statistical analysis of, then these problems need something that is sort of the linear segmented analog, and it turns out that's going to be our sensitivity approach. So think about price sensitivity, we are really going to be thinking about a way to consider a set of prices that start on GDP line 1 and give us combination B. And what we're really going to be trying to measure is how big a swing, how big of a rotation do we need before we'll make this change? How sizable does the price rotation need to be before we can move from B to C? And then again, if we started from point C, what price rotation would jump us back to B, or what price rotation would move us down to D, right? And so we'll get measures in both directions, and they'll really be about how much can prices change before we want to make an adjustment to our best plan. Right? So these best plans, if inertia is a thing in physics, well, in these linear approximate problems, inertia is an even bigger issue because small price changes are not going to cause us to move. Okay, so we can think about price sensitivity really being about measuring some kind of distance, but we'll just think about it in terms of hold this price constant, start changing this price. How much does that price need to change before B is no longer our preferred choice? And that's what we're going to be measuring in terms of price sensitivity. On the resource side, we have a little bit different approach, or we have something a little more conventional. So, returning back to our sort of curved, normal production possibilities frontier problem, we said that you could think about an economy that either had some kind of policy-related labor change or some kind of capital change. You could even think about a land change where maybe you allow more forestry to be removed out of sort of native forest into managed land status, so that you're actually, even if it's just logging off of forest that were not previously logged on, that's like an increase to the economic activity on land. And so, but always in these problems, what we're thinking about is, if this was the feasible options before, and there's been some change to the feasible options, if I re-optimize, what do I expect the impact to be? Prices didn't change, but they matter, right? So the prices don't change, but once we find out how the resources expanded and how those things are used, those resources that are expanding are used in output, we should be able to come up with some economic interpretation that depends on the prices. Well, it turns out, we're still not going to go back and do this Lagrangian problem, but if it was curious to you before, maybe it still is, and maybe it still will be after I bring this up. But the entire point of writing this problem this way and sticking this capital lambda in front of G is to get a measure of what happens if that constraint gets relaxed. Okay, so remember up here, G is this frontier, right? It's basically this limit on total output. QF and QN combined, G is going to tell us how far that can go. Well, if there was some movement in resources X that allowed a little bit more production, then that's what this term right here measures when you solve this problem. This lambda tells you how valuable is that. It tells you how much profit you can gain, or how much GDP you could gain through a small change in the endowment or in the labor available. For us, it's going to be kind of a similar approach. So instead of doing that sort of lambda mathematical solution, we're just going to it turns out the linear programming algorithm for solving can calculate the same thing, and we could actually solve it the same way. And in fact, we're actually going to be a little bit more informative. So while this curved function, back here, doesn't really give you much information to go on, right? How does the labor constraint actually change this? The way I've drawn this new constraint compared to the old one, it's like every resource had some common percentage increase. Well, but in our case, we know that this is sort of the capital region, and this is sort of the labor region, and this is the land region. And so if land expands, then we expect this line segment to move out and the other two to do nothing. If labor is expanded, we expect this line segment to move out. Capital, this line segment. And so in this linear segmented problem, we actually know quite a bit about resource sensitivity, and it's one of the reasons this is such a popular sort of output planning model. The LP gets used so much because it lets you quickly consider the alternatives and the valuation of expanding your labor force or expanding capital, machinery, throughput, however you want to think about it. Okay, so we have this assumption. We've solved the problem already. We've got point B. That's the best combination. And the extra information we get by knowing B is the solution is that we're using all of the capital and we're using all of the labor. We are not using all the land. And so we call those the binding constraints. Those are the things that cause GDP to stop right there. If there was more of either, we know that we could probably improve GDP. We know the economy is efficient even though there's land being not used, because we are at the highest earning feasible combination. Okay? So I have this question here. Should we consider a more detailed model that has more uses for land? Well, maybe, right? Maybe food versus non-food does not give us a clear enough picture on the land demand side, right? So we might want more detail, and that's obviously one of the things we're going to, once we learn the technique, we're going to learn about implementing more details, more specific constraints, because if the value of these problems for production and planning is in the idea that you get you get very detailed information out of the solution about what the value of expanding capital and labor would be. Well, think about what it would be if you had a specific type of labor, manual, low-skilled labor improvements versus managerial labor, or labor, if you're thinking about a farm, during the harvest part of the year versus during the spraying and maintenance part of the season versus planting, right? So if you split all those out into separate resource constraints, you know what the value of those are separately. And so that becomes an important sort of economic question. If you think back to the sort of first picture I showed you when we met in Bloomington, I talked about solving a model and then going all the way back and thinking about, can I implement this better? And so that might be one of the things we would think about from this, revisiting our assumptions, thinking about what kind of other sort of resource detail might I put in a problem like this. Let's think about our problem again on this GDP context, though. Immigration that expands the labor force, well, that would move this segment out. We would expect to get better GDP, right? Because we would no longer be binding at point B, we would be binding at some point that sits outside of there. International finance, so we get more capital inside the economy. Well, that moves out this segment. B is no longer best because B is now going to be not at the corner. And then, of course, you can move down here and think about if forest conversions allowed so that we can get a land expansion. That would move this segment out, and unless it moves a lot, it's not going to affect this because it's not going to change B being the corner point. Now, you can imagine a huge land expansion that might come into play and intersect out here and create a new corner, but that's too large a change. We're trying to think about small marginal changes. And then, of course, the sort of key result is when we're doing sensitivity, if you have a non-binding, that's a solution, but it really something that is non-binding, a constraint that is non-binding in the solution, any kind of policy or questions about it should show up as no impact at the margin, right? So you'd have to think about really large changes. Yeah, and so let's pursue this just a little bit more and think about this the labor constraint. If we expand it out, what happens? Well, the corner points B and C actually both disappear. So that segment gets moved out, and it looks like something here, and now you end up with the new corner point here, the new corner point here. You can see I've drawn this small dash line to be the new intersection of the new intersection from the labor constraint with the capital and land constraint. The GDP line, the prices haven't changed, and it looks like you would go from point B to whatever this point right here where I'm holding the cursor is. That would be the new solution, right? So you still keep moving in the direction where I'm going to exhaust capital and labor use, but the corner point's going to be different, and we're going to be able to calculate a new GDP level, how much labor was added to the economy, and it gives us a very easy measure and an important measure. Right? It's a cost benefit, especially if if getting new labor into the economy means that we are having to make some kind of investment, right, in training or whatever cost it takes. Like if it was an immigration type policy, then typically we think about there's national public goods that have to be accounted for when the population grows. And so you could think about the cost benefit. So you want to know the benefit in terms of GDP, and you can measure it up against the cost. But anyway, that's how we would do that. So we get this new segment, we would resolve and find this corner point. The new GDP level would be something that we get reported to us from the new combination of non-food and food. Okay, so we evaluate it, get the new GDP level, and you want to know what the policy's worth. Well, you just take the old GDP found from point B, the new GDP found at this new point, and you just divide it by how much was that change in the labor force, and you'll get a per labor unit measure of the gain from the policy. And that's what we call a shadow price. Okay, and so if we backed ourselves up, these lambdas, this lambda in this problem is called the Lagrangian variable, but the Lagrangian variable gets interpreted and it gets solved for and interpreted as a shadow value on the resources in the economy or in the problem. And it's the same thing we get here. Whoops. If you expand this out, calculate the new minus the old, divide it by the quantity adjustment, you're getting a per unit value. It's the shadow value. And what is important about it, or what's sort of interesting about it, is you don't actually have to solve any of that new stuff. You don't have to make all those changes, even though that's how we'll learn it in the in class. We'll go through a lab where I make you make all these changes right after this lecture. It's actually something that you can solve, that gets solved for simultaneously with the base solution. So if the basic solution here is this amount of QF, this amount of QN, whatever level of GDP goes with that, and these two constraints are binding, well, there's some extra information that comes with that solution. It actually comes from the algorithm called the simplex method. There's some extra information. It's called the dual side information that gets solved for at the same time. And what it is reporting to you is, if this is this is a binding constraint and this is a binding constraint, there's a shadow value that says any little movement of this constraint or this constraint can be associated with a change in the total GDP, and that'll be calculated for you. And so really it's what's the marginal adjustment here. So just like we would get from this curve problem, what would a small increase in any resource be worth from that lambda value? We'll get it calculated here in our algorithm that we use, and Excel will report that. So we have two versions of sensitivity. One, what happens when the GDP line gets rotated or it has its slope changed, or in economics terms, prices adjust, and then the second one, when resources adjust. It turns out, you get sort of the opposite thing. When we assume prices adjust, how do we adjust the quantities, right? What kind of quantity adjustment can happen? And then when we think about adjusting the quantity of resources, what kind of pricing can we get for those resources? What should we be willing to pay to get new things? So if you think about our farm problem, one of the solution pieces that comes out of it is not just the plan, but it's what is the rental rate? What's the best rental rate for additional labor or for additional land? And that's the value of sensitivity, and that's going to be our major topic for Module 3, but also a topic we're going to explore some in the next lab. And as you start working through minimization problems, you'll see in the part of that lab as well, you'll see how those valuations depend on the type of problem we're working on. With that, that's going to close out our lecture series in Module 2. You've got some lab and assignment work still to go.